Hi everyone and good afternoon. Welcome to this workshop jointly organized by Pledger and Rainbow projects, and in particular by Lara and Panayotis. Very shortly, the agenda for today is an introduction by them on the concept workshop, and then there will be a first part mostly focusing on Pledger outcomes, where we will have Francesco Iedanza from engineering that will provide the view on the activities they run inside the project on resource optimization. Then you have Ioannis Saris from the Intrasoft company that will provide an overview of the data ingestion activity in Pledger. And then we will have Antonio Castillo Nieto from Atos talking about discovery and orchestration of resources in Pledger, and Estela from I2CAT presenting cross-domain networking, slicing, and orchestration. In the second part, we will cover the recent outcomes from Rainbow, and in particular, the Panayotis, the director of Ubitech, and coordinator of Rainbow project, will provide an overview of the core functionalities of the Rainbow platform, while Moses will, from the University of Cyprus, will provide an overview of the activities in relation to Fogify and data analytics. And then we'll have some time for question and answers. And now I give hand over to Lara and Panayotis if he joined us meanwhile for the welcome.
1 second, sorry, Federico. Sorry, Lara, I will take less than 1 minute, just few seconds. Hello, everybody. I just wanted to give you a couple of logistic information. The meeting is being recorded. So please, I would say if it is not acceptable to you to this for not being recorded, then I would ask politely to leave. The other is, please use the chat for questions. Please do not, and at all times, for the participants, please keep yourself on mute and the cameras off, and only accept the speakers when they are talking. Please use your camera, turn on your camera. That's all from my side. Lara, please go ahead.
Okay, thank you, Amrita, and thank you, Federico, for the introduction. And thank you, everybody, for coming today. As you will see in the agenda, there are real new challenge that we are facing from the edge computing side. Is not only about the different heterogeneity of the devices that we're facing at the IoT level, but also at the edge level, and the location of these devices. And here appears the concept of near and far edges, depending on how far or near are them to the edge of the network or even to the data center. So today what we want to present is the different approaches from the Pledger project and from the Rainbow project about how to deal with these informations, because it's not only a matter of having the resources, but as they have limited functionalities or capabilities, we need to select the better deployment scheme, where to deploy or where to execute the different applications. At the same time, we have these network connectivity issues because not all devices are available at the same time. The network cannot be stable all the time, and even the amount of data to be transferred will vary from one application to another. So this is something that we have to do. More specifically, in the Pledger part, what you will see is how we deal with this network connectivity or what we are doing, how we manage or meta-orchestrate the different resources, taking into account the different application layers that we have, but also from an industrial IoT perspective, what can be done and how we solve these issues, as well as how we benchmark the different applications and providers to better select the mapping between the application and the infrastructure. On the other hand, from the Rainbow perspective, you will see that they are focusing on the data analytics part. That is also crucial about how to do or how to decide where to do the execution. And they will present the core functionalities of the platform that they are developing. And that's all from my side. If you have any question in general, if not, I think I can leave the floor to the first presenter from the Playtech project.
Hello, this is Christina Stratigaki from UBTech representing the Rainbow project. As far as I can see, I cannot start my video, but I want to show to everyone that I'm not Panagiotis Gouvas, actually. Panagiotis Gouvas, fortunately today, he's expecting to be a father, so he wasn't able to join today. I am also participating in the Rainbow project. Actually, I'm leading the coordination of the project since UBTech is also both project coordinator and the technical coordinator. I'm here with two colleagues of mine that will undertake later on to do the presentations of the core fog functionalities and also with regards to the Fogify data analytics from UBTech and UCY. So I totally agree with the concept and what are the challenges that both projects are willing to solve, let's say, or tackle. And the Rainbow project, in a few words, is trying to design and develop an open, trusted fog computing platform that will facilitate the development, orchestration, and management of scalable, heterogeneous, and secure IoT devices and cross-cloud apps. We are trying to do so and test this approach of Rainbow in various real-world scenarios, in automated manufacturing, in connected vehicles, and also in critical infrastructure surveillance with drones. So without further ado, just a short introduction on my own, and sorry on behalf of Panagiotis that he wasn't able to join today, but it is for a good reason. We will be there, the rest of the UBTech team, along with our UCY colleagues, to do the presentations and participate actively in the Q&A session. So let's hope that we will have a great meeting. Thanks.
Thanks a lot. I think we can hand over now to Francesco to present the activities on resource optimization in Pledger.
Let me share my screen. I think you can see my screen, right? Can you see my screen?
Yes, yes,
okay, thanks,
it's on.
So, okay. Thanks for the introduction. One quick introduction by myself. I'm Francesco Iadanza, Senior Researcher in Engineering Informatica. It's an IT company founded in Italy now with 40 offices around the world and around 10,000, 12,000 employees and 400 researchers. In Pledger, we have two main contributions on technical activities. One is about benchmarking, that where we had already a session in March, still on hCloud. So if you are interested, you can probably get the recording. And the other is about the DSS that I'm going to present you today. So as you might already know, the goal of this project is to deliver a new architectural paradigm with some tools in order to, for edge computing providers and adopters, in order to couple the benefits of edge, so like the low latency and also the robustness and resilience of cloud infrastructures, This is a big picture of all the tools and services that we are providing. Basically, today we will focus on this part that is about the management orchestration with the DSS that takes the allocation algorithms. And as we will clarify in a moment, it gets lots of information from the profiler, the benchmarking, and in turn on the metrics that are used underneath. So the main problem that we're trying to solve with DSS is to understand which action we need to do in order to fulfill some QoS for my application once it's deployed on the edge or in the cloud infrastructure. So we basically take the QoS metrics and the violation that we get from them as a feedback on the activity that the DSS takes. And the idea is, of course, also to include all the other information that I briefly mentioned before. That is not only the identification of the key metrics for the QoS and QoE, but also the measurements, the monitoring of the SLA violations, and the warnings in order to be a bit more proactive in the decisions. Rank the deployment options so that we can leverage on the infrastructure variety, because we, of course, in the edge need to be aware of the huge capabilities of the very different devices and their different hardware, and also other domain information that might be used for the possible ranking. And then, of course, in the end, choose the best infrastructure and node for a given application. As we can see, this is an interesting challenge. But first, let's put this DSS in the center of what are the main components that I mentioned before. So it's basically, let's say, in the center of some flows, like receiving from a component that we call comp service, where we manage all the information related to the edge device variety. Then we leverage on the benchmarking and app profiler in order to be more efficient into the choice of which node to use for the allocation of an application. And then, of course, all the monitoring part and the SLA management with the warning that we need to receive in order to take the appropriate decision that in the end will be actuated by the orchestrator. So basically, the scenario that we try to focus mostly is about when we have private, scarce, and diverse edge resources. This is the most important scenario for us. And we basically try to focus on this scenario first, asking the service providers which are the preferences he wants us to have and the priorities in order to have these deployments. This is a way, let's say, to leave some floor to the service provider in order to express some coarse-grained preferences and include some domain knowledge that might not be completely covered by the sheer hardware assessment, let's say. I mean, an example could be not just focusing on location, which could be in a way retrieved somehow, but also other information that might be of some importance to the service provider. Then within these choices that are coarse-grained, the DSS acts autonomously. So this is basically the way the DSS works. Then, of course, there is the monitoring and the classification of the data with the app profiler and the benchmarking, and the retrieving of warnings together with, along with the violation from the SLA in order to have feedbacks on how we are proceeding. To manage all these activities, basically the DSS creates resource allocation models based on thresholds in order to understand which are the current capability of the underlying infrastructure. Then change the resource allocation and threshold in order to reduce the waste, especially on the edge where the resources, as I said, are scarce and are mostly fixed. And then, of course, if it offloads whenever it's not possible to keep the computation on the edge. Of course, using these deployment rankings as a high-level guide, as I said. Now, just to give you an example, the first question that we try to solve is how to manage the edge resource variety. This is quite straightforward. As you can imagine, it's more a matter of labeling the information. This labeling, these features that are labeled are taken either automatically from different tools that allows the automatic assessment of the hardware availability, like CPU models and GPU models, which might affect the proper allocation of specific computations. And also some labels that are domain specific, which, as I said, are mostly into the domain of the knowledge of the service provider, like the location, but could be also other things. This, in the end, provides, as I said, some high-level guidance. And in this example, it's very easy to understand that we define, for example, regions where we want to prioritize possibly the deployment on one. Then if it not, we can see, okay, we want to move on this other region, maybe on nodes that are more important for this application, and then move to the other. So this is a high-level guidance that we give to the DSS. And then it starts, let's say, the pure computation of the DSS. So the first thing is to deal with the edge resource allocation. We inspire to Kubernetes QoS model that is based on resource thresholds with minimax. This means basically that with min we represent which are the resources that are guaranteed to be assigned to a specific application. And of course, this can impact which application can be hosted on a limited resource infrastructure. And similarly, the max is the total amount that of resources that an application can use. And this is, of course, also impact which application could be evicted using the Kubernetes terminology that would lead to SLA violation. Here I'm talking about Kubernetes QoS model, but as I said, we don't support just Kubernetes, but through the orchestrator, we try to be infrastructure agnostic. So let's say we inspire to this model, but we wanted to provide something similar also to other infrastructures. In the end, the general idea is to keep the thresholds as close to the actual needs as possible. And I mean, this could be quite obvious on the cloud, but on the edge, this becomes completely different. I mean, the semantic of some resources like CPU, as you can imagine, is completely different, because if on the cloud we say that an application should use at max 200 millicores, it gives an idea of which is the required power. But on the edge, 200 millicores depends on the kind of the CPU that is available. So, I mean, it's mostly important that we try to adjust these thresholds whenever we find that are some resources that are completely different. Of course, to do this, we also leverage on the benchmarking, which gives us some estimation. But as you can imagine, this dynamic adjustment that is also called like bean packing in Kubernetes is something that is more relevant on the edge. So basically, in the end, as I said, use the SLA warning in order to decrease these resources, and use, and if of course there are no more resources, we offload. Then we now enter into the choice of which application to optimize first, because as we said, the resources are scarce, so there could be some competition. And of course, we need to prioritize also the activity in terms of allocation of resources. Of course, this is done using some weights, some scores that we compute based on the priorities that we have on the application and how severe were the violation. And of course, this also takes into account another, let's say, side issue of possibly scaling up and down or in and out the application. That is of course, the attempt not to disrupt any service, and to have, once we want to resize a service, also to manage the time to boot the server on the other, let's say, instances, which of course needs to be measured in order to prioritize those, not only those that are the biggest, maybe that would free more resources, but also those that are faster to be released. And this, of course, is something that we need to measure, and we do it. Then there is the other key point is about how to choose among multiple options that we have at the same ranking. Because as I said, these rankings are a way the service provider uses to give his preferences, but within these preferences, there could be some autonomous decision, and that's where the DSS comes in, using the benchmarking and the app profile. So basically, we profile the application and know which is the best benchmark for a given application, and this gives us, starting from the metrics and the scores that we get from these metrics, this allows us to choose which is the best application, the best node that should host a specific application. Then there is another optimization that we use, that is how to choose within the same edge nodes, those that could be more, let's say, important for a specific application that might suffer when, let's say, that have low latency requirements. In this case, we measure the node-to-node latency, and in this case, we can prioritize the nodes that have lowest values, so that even if we are in the edge, and while, I mean, when I talk about the edge in this case, I'm thinking more on a more distributed environment where we have edge, far edge, let's say, devices that might not be all in the same place, but still considered on the edge side. In this case, we use the node-to-node edge as an additional input in order to prioritize where to place specific application. And last but not least, let's say, as you can imagine, this DSS has some autonomous decision taking, and also is guided by, as I said, by the ranking provided by the service providers. At the same time, there could be the chance where we want to create some autonomous, let's say, some custom automation, because it could be something that represents some specific knowledge coming from the service providers. In this case, as you can imagine, the DSS is not just a tool that you use using the UI, but also provides some REST API that you can invoke through a tool like Node-RED, which we integrated. By integrated, I mean we created this very simple custom connectors with our DSS, so that you can create your custom automation in case you need it. So this, of course, goes outside the optimization, but it's more on the, let's say, the scheduling of resources, trying to include also some business logic if needed. So just to close, I'd like to say that we are at the end of the second year, more or less, so there is still some work to do in Pledger. And the next step will be to finalize this integration with the use cases and also validate the algorithm also with I2CAT. Then we plan to include the far edge devices to support the edge-to-edge offloading based on the edge node latency that I mentioned before. Also, given the fact that we are going into our use cases to have this kind of devices, it will allow us a more possibilities to test this algorithm. Then the other challenge is to include energy benchmarks on the edge devices in order to optimize service allocation. This is still on progress. We need to still to work a bit on the modeling, and we'll then probably include this optimization also. And the last part is more a challenge, let's say, that is this experiment on the distributed load balancing in multi-cluster. I mean, the general idea here is to include the weighted load distribution as a way to manage the proper allocation of services within multi-clusters. So let's say, just to move forward and not stay into the idea of offloading or not an application, but also thinking about using weighted traffic so that we can steer a part of the traffic to the edge and the other part on the cloud, in order to have a more continuous deployment of services and not make it discrete, let's say, so a bit more continuous in this way. But let's say this is the final challenge that we have in our plan. I mean, this is probably the most interesting one. And yeah, I think it's mostly all from my side. I left a few minutes in case you wanted to ask some questions. But I see also from the general agenda, maybe we will have some at the end of all the presentation. I mean, Federico, as you prefer. It's up to you. If you anybody want to ask any question, please feel free to do it now, and I can answer either now or at the end of the presentation, as you prefer. And that's basically.
If there is any question, I think it might be good to make it now. On my side, I'm just curious to know if this is let's say more centralized at the time being, okay, but if you are also looking at ways to somehow take decision on the optimization, and that then of course will become more local, but also at the edge.
Yeah, this is a very good question. Ideally, the natural evolution of this tool would be to be decentralized, also because we already support directly Kubernetes, and as you know, it could be used also as a local orchestrator on the edge. It wouldn't make many difference to, I mean, in terms of extension, it would not be so difficult, because this kind of optimization right now have a view over one or more infrastructures. So we can just take this and apply to one smaller one that could be considered edge, adding some synchronization, of course, in order to overcome unattended disconnections. But of course, this needs more thought. But I don't see, let's say, very complicated to do. That could be another step to do. I mean, there is still time, and yeah, we could also test this kind of scenario. That I think it would be very interesting.
I think there is also a question from Reza. She is asking if in the edge-to-edge offloading, if the nodes are directly interconnected, or if these needs to go anyhow through the cloud.
Yeah, let's say that the kind of scenario we have right now assume that, of course, there should be some connectivity already in place. When I talk about edge-to-edge, right now I'm thinking about concrete use cases where we have nodes labeled very differently, but located in different places, but all interconnected with each other, so there are no connectivity issues in between. Of course, I mean, this is also part of what we mean by infrastructure. Let's say this has been discussed also in another meeting. But let's say, to my definition, I would say that yeah, I would consider different infrastructures, maybe two edges infrastructures, but still there should be some connectivity in between that allows this connection between pod to pod. There are many tools that allows this if we want to connect multiple infrastructures. Right now we are testing a lot, like Submariner, Istio, Scooper, many others. There are pros and cons, and also Linkerd. There are pros and cons, and also there is some right now some limitation due to the support of smaller CPUs that are not supported in some of these tools. So we are trying to use one approach that covers as many cases as possible. But in the end, once this connectivity is in place, this should, this should be transparent. One last word is, of course, that in case of low latency requirements, my doubt, because I saw some reports about the added latency, is that if we have two edge infrastructures that are separated and need this kind of tools, probably the idea of doing this offload from edge to edge and have part of some services on one and some on the other doesn't make much sense, because the latency added by these tools is too high. So definitely for very low latency requirements, I think it would be quite obviously necessary to have a direct connection between nodes. I don't know if this answers the question.
Okay, yeah, I think Reza is happy. So thanks a lot again, Francesco. And now I hand over to Ioannis, who is going to talk about the edge to cloud IoT data ingestion. He's a senior researcher at Intrasoft and working on different distributed systems.
Hello, can you hear me?
Yes, Ioannis, we hear you.
I cannot start my video, however. Okay.
I think it was because maybe it was still up the sharing from
okay.
Francesco. Okay. Try now.
Start my video. Okay. First of all, can you see my screen?
We can see you, no. But not yet your screen.
But not yet your screen.
Okay, just give me a moment. Now?
It's coming up. It's up.
Okay. Good. Thank you. Hello everyone. Good afternoon. I'm Ioannis Saris. I'm currently working as a senior software engineer at the Department of Research and Innovation Development of Intrasoft International. Intrasoft International is a leading European IT solutions and services group with strong international presence and expertise, offering innovative and added value solutions of the highest quality to a wide range of international and national public and private organizations. The company employs more than 2,200 professionals, over 50 different nationalities, and mastering more than 30 languages. Today, I am going to present you the edge to cloud data ingestion here that we are facing Pledger, a topic that we are currently working in our project. So before we start, I would like to begin with the scope and the main objectives, let's say. So what we are trying to solve here, actually, current approaches on edge computing are not sufficient, let's say, to address the massive usage of edge computing, especially in the frame of large IoT deployments in smart cities and industrial applications. The main goal in such scenarios is to ensure that the overall offered quality of service fits the application needs over the edge or edge to cloud deployment. At the same time, speed and latency issues have been identified as the top barrier in this domain, while cost and reliability are the top and the second most important factors for evaluating edge and cloud services. Of course, there are specialized and expensive also solutions that are preferred over generic edge computing or cloud infrastructures. So the Pledger project aims at delivering, let's say, a new architectural paradigm and a tool set that will pave the way for the next generation edge computing infrastructures, tackling the modern challenges faced today and coupling the benefits of low latencies on the edge with the robustness and resilience of cloud infrastructures. Something which is important to note here is that migrating to a cloud infrastructure and even more to edge fog can bring cost, performance, and strategic, let's say, advantages. But it should be performed, let's say, with due diligence and careful consideration. So let's pass to our main topic here and why edge to cloud matters, let's say. First of all, we have edge devices that have limited computation power. We want to keep, let's say, the cost of edge devices low. Also, there are industrial operations are often located in harsh environments where only specific hardware can resist on those conditions. And for many companies also, connecting to remote assets and securely transferring operational data remains, let's say, a significant challenge. So by centralizing the data on cloud, will pave the way for next generation, let's say, it's computing infrastructures where sophisticated, let's say, ML solution training will happen and will lead us to take smarter decisions, let's say, on the cloud as well, or have the training, let's say, on the cloud and then pass to the edge, the algorithm, and so on and so forth. Pledger, let's say, offers a unique approach for solving this edge to cloud secure data ingestion. The solution is comprised of two software stacks. The first one is placed on the edge. Our main key partner, let's say, here is Phil. It's an Austrian company that offers a smart factory solution platform called Cybernetics that digitizes the entire production process on the edge. As you can see, the complete architecture of this platform is presented on the left of our screen. Let's say we have a control cabinet where the automation, let's say, here is done by using some PLCs. And this cybernetics platform is connected to those PLCs, let's say. There are some connectors here. Then there is some data normalization, let's say, approaches that happens in order to convert the data to standardized JSON format. And then we pass to, let's say, the local message broker that the platform has for having some dashboards and based their, let's say, decisions on this dashboard. This platform, we have quickly identified that this platform hosted on the edge requires extensive amount of computation power in the cloud. And whenever, let's say, the SLAs that are going to be defined, let's say, in the context of our project are not met, computation and secure data transferring need to happen on the cloud. So, as you can see, the second one, stack that we have is hosted on the cloud, and this one of our components, which is called Stream Handler. Stream Handler is a platform that is designed by Intra and allows this secure data transfer to happen with a secure, fault-tolerant, and highly available manner. Upon Stream Handler, different data processing steps may be added that will allow also machine learning and data analytics, let's say, to improve the performance and the quality of the existing results. So, what is Stream Handler? It is a distributed event-driven streaming platform based on Apache Kafka with, among other advantages and features, built-in capabilities for straightforward horizontal scalability. So why using Stream Handler in our project? First of all, while other approaches also exist, like message queues, ActiveMQ with the enterprise integration patterns implemented in Camel and RabbitMQ, with exchanges also and routing algorithms respectively. These solutions can potentially accumulate, let's say, the business logic in the message queue and make solutions complex to maintain and affect, let's say, the scalability. In Stream Handler, the business logic and solutions are implemented by incorporating distinct loosely coupled components which communicate with each other via topics. Another advantage of using such a solution is the ability of multiple clients being able to read the incoming information from the same topic with different offsets per client, the simultaneous processing of data that are entering the system from multiple clients, and the ability also for clients to process again and again and replay the streamed data. In the streaming core platform, as you can see here in the picture, we have multiple brokers that have been set up and running. We have also some components additionally the connect component, Kafka Connect type of connectors that reside in multiple workers. We also have a platform administration dashboard which contains Prometheus data sources, Grafana dashboards, and panels which are meaningful for monitoring the cluster and looking into, among others, CPU usage, RAM usage across brokers, message rates, that is information that is coming in and out of topics, and other type of information like total number of messages within a topic, producers and consumers, etc. So we have also the security management component, which refers to the fact that all the communications across all our components within the cluster are done in an encrypted way by issuing certificates which are issued by the security management of the cluster. We have also components like schema registry that can be used to maintain schemas of the messages that are being communicated inside the topic, and also you can have the connectors themselves that either reside on the connect component or can be a producer type of connectors that take information from an external data source and load it into topics. Of course, what we can see on the right-hand side is that, let's say, engineers and data scientists can also go on and develop, let's say, applications that interact with the data sources available by reading and writing into topics. So these are the building, let's say, blocks that allow these people to start developing data processing pipelines, as they are called, in which one application is taking some information from one or more topics and combining that information in order to solve a problem or provide a part of the solution. Then this writes back this information on another topic, and by chaining these small components, you can end up by having a data processing pipeline which reacts live in events, and then you can have all these little building blocks communicate with each other, and in the end receive the answer to the business problem that we are trying to solve and are trying to solve these components. The stream handler security, let's talk a little bit about the security of our solution, because we are talking about data here. We have 4 layers of security. The first one is the infrastructure security. This is principally the security applied on our VMs that we use in order to host our solution. Then the second level of security is the encryption of the data. We have encrypted communication among all, let's say, stream handler cluster components and among the clients of these components. Our third layer is the authentication, is that by using SSL, we are using SSL certificates to authenticate our clients. This allows our producers and consumers to authenticate to our stream handler platform and verify their identity. This is principally done with a certificate authority that signs certificates of trusted nodes and IPs, and the client's key stores and trust stores are distributed to the clients in order to be able to access the cluster. The final layer of security is the authorization. Kafka broker can run against, let's say, access control lists to determine whether a particular consumer or producer is authorized to write or read to some topic. So let's pass also to some, we have also some other interesting, let's say, use cases, let's say, by using this platform. What I would like to showcase here is that, let's say, our solution, let's say here, the solution of Stream Handler has been used in order to ingest a large amount of data, let's say of Vodafone Innovus, let's say, you have achieved a load to 100 gigabyte of historical data to be loaded in the cluster in less than 4 minutes with almost 5 million messages per second. And what I would like to showcase here is that this is showing, let's say, the amount of information that these technologies can handle. It should be mentioned that we have seen, let's say, by using 3 brokers of, let's say, 32 gigabyte of RAM and producing simultaneously to a topic that has 9 partitions, we have observed the loading of, let's say, CSV information like small messages of GPS points of the tracks here that exceed, let's say, the 5 million messages per second. So you can understand that by parallelizing your task and by choosing to use these technologies on partitioning schemes in a clever way, you can end up loading information which is inside CSV files of vehicles moving around that spans in a couple of years. You can end up loading that information inside the topic in something like 4 minutes. So if you consider that at the same time, you can have some consumers of that information that would in parallel process these messages, then you can begin to see that you are setting up a system that can indeed scale horizontally, and you can introduce more hosts if necessary, which is very important. And what is also equally important is the fact that by splitting the processing load across different CPUs, what you have here is something that solves a problem which can even be a big data, let's say, problem. Regarding, let's say, here it's a small comparison with some already popular solutions, our solution with some already popular solutions. What I would like to highlight here is that we are hosting our Intrasoft solution, hosting his solution in Hetzner public cloud provider. And we can see that Confluent is almost 10 times more expensive than ours. There are some comparisons here that we have done, and the Cloud Karafka is less expensive, of course, compared to Confluent, but it still remains incomparable to what we have achieved, let's say, and the results that we have achieved. So this was our data ingestion, let's say, platform that I presented you. And let's say the conclusion is that the remote connection and secure data transferring of operational data, let's say, is still challenging. The edge application of loading needs to be done carefully, and when is needed, appropriate SLAs need to be defined for that. And we are currently working on that pledger. And also, a last point is that you have to enable, let's say, the data ingestion, intelligence gathering and control at the place where it is needed. So if you want to learn more, there are the pledger edge to cloud use case also in our site. And that's all from my side.
Thank you very much, Ioannis. Is there any question from the public? Okay, just a curiosity. I mean, you showed in one of the last slides the cost. Are you comparing these costs for, let's say, the same processing capacity? Or,
yes, I compare this with the same capacity, and the results are incomparable. Of course, in Confluent, you can have Kafka as a service. Okay, here we have, let's say, a solution that is built on an infrastructure as a service that we choose, which is Hetzner, and will build on top our solution. So, of course, it is less expensive because we we have only the cost of the infrastructure. But also, let's say in the solutions, let's say that, let's say the Cloud Karafka has, you can have, let's say, 3 brokers, and the brokers also are hosted on the same machine with the zookeepers, something that, which is not, let's say, a good architectural also design. In our solution, let's say we have chosen also to put the brokers and the zookeepers, let's say, on different machines for having high availability. Of course, this is going to be changed as well because Apache Kafka is changing at the same time, and is going to remove, let's say, this completely this zookeeper thing, and is going to have his own implementation of Corm, let's say.
Okay, thanks a lot. I see there is a question by Sean about the security features, and he's curious about the fact if these features are automated or manual setup are required.
Regarding the SSL certificates, first of all, yes, you have, for example, if you want to read or write on the topic, you need to get a certificate from Apache Kafka cluster. For the moment, we have a manual setup, but this can also be automated in the future, let's say. We plan to do that.
Thanks a lot. If there is no additional question from the audience, I think we can move to Antonio Castillo Nieto from Atos, who's gonna cover the way Pledger is managing the discovery and orchestration of meta resources.
Hello. I cannot share my video, but I can share the screen. I don't know why I cannot share my video.
Oh,
wait a second. I try to enable it.
Don't worry.
The video.
You don't need to my fate.
Okay. Yeah, you were up.
Okay. Let me share my screen.
Good.
Okay. Okay. Do you see my screen? Yes.
Yes.
Okay.
Yes. Yes.
Okay. Let me a short introduction of me. I am Antonio Castillo from I am a research engineer for Atos Research and Innovation. I participate in Pledger core platform project. Okay. Let me introduce some interesting data about resource in the continuum, about the increase of connected service and creation of data. It's not new for us, but maybe the last one is the more radical changing our mindset, because now the data is going to be processed in the origin of the data in the edge or when in the place you produce the data. Okay, it's a new paradigm. It seems something that is going to change many things. And let me say about digital transformation. You know that digital transformation is not about technology. It's about how to change or transform the business in order to make a company data-driven. Not only the business area and function of the company, but all the company corners about take decision based on data. Okay. Now we are in a moment that there is a convergence of an edge, IoT, and network connectivity. Edge computing is a key technology for IoT, 5G. We have several challenges here: decentralization management, heterogeneity, and volatility of the resources. We have the solution to combine connectivity, edge, and multi-cloud for get that challenge. So what the future? The future for us is swarm managers among IoT, edge, and cloud. We are talking about massive distributed computing models dynamic ecosystem of cloud and edge device, allowing operation and interaction to adapt according to the context, improving efficiency and reliability, enabling ad hoc collaboration, optimization, delivery of sharing of information, seamless management of multi-cloud edge and IoT elements to complete the service orchestration. And what can be done? For us in Player, we can see at least 3 points to deploy our workload or our application or our service that compose the application. We can see public, private cloud, on-premise data center, and edge side. In public private cloud, we can use virtual machine, Docker, Kubernetes cluster, and functions and service platform. And on-premise, we can see bare metal, virtual machine, Docker, and Kubernetes, and not usual function as a service platform, as we expect to see more in on-premise data center. And in edge side, we use bare metal for some Raspberry Pi or some hardware with computing capacity, virtual machine, and Docker. And not usual to see Kubernetes because sometimes you only have a node or a constrained infrastructure to run. Maybe in the future, Amazon is doing, we can see fast, okay, the function as a service in the edge. Okay. What is Player Orchestrator? Player Orchestrator is a tool for managing composed service lifecycle in multiple environments, managing service requests, orchestrating the share of the best resource of executing service, and manage multiple cloud edge cluster and device. Here we can see an internal architecture of components that compound the orchestrator of Player. We have several engines, one for deployment, one for scaling, one for placement or migration, one for infrastructure management, provisioning. This component is a translator from every order or command that the Player platform needs to the underlying infrastructure like Kubernetes cluster, micro Kubernetes, Docker, Swarm, virtual machine, hypervisor, etc. We have an abstraction layer in order to make a operation of the underlying infrastructure, in order to separate the technicality of the infrastructure from the platform. Okay. This one is another view of the thing. Now we have here the orchestrator is a component of many services, the orchestration service that we see in the last slide, that station service that Francesco told in the last presentation, the monitoring service and the service layer manager, the SLA manager. All these components are working together in a choreography to make an orchestrator. You can see here the two paradigm combination to create the orchestrator. We can introduce data for this platform for graph user interface, REST API, using Kafka event-driven application, using the string handler that Johannes told us. Of course, with Tosca or some description file. Okay. The output of all of these topology or application translate to operation to Kubernetes cluster or family of based on Kubernetes, like K3S or micro Kubernetes, OpenShift, every distro Kubernetes, Docker REST API, or even other container engine. For now, we implement in Docker, but we plan to implement containerd or even micro IO. And some virtual machine hypervisor using Ansible, Terraform, Packer, or some tool to isolate the private API of the hypervisor from for the orchestrator. Okay. This is one regular day of the orchestrator platform of player. The first thing we have to do is to configure the infrastructure and the application topology and dependencies, and introduce the param of the quality of service of that application. The day 0, we deploy the application in one location, and the best location we have in that moment. We start monitoring the application based on the quality of service metric we choose. In case that some quality of service level doesn't fulfill, there is a alert system that sends a violation to adaptation system, and the adaptation system takes some decision based on machine learning or some rule-based database. Okay. That's all for me. Any questions?
Thanks a lot. Is there any question from the audience? Okay, I do have a question, and so one of the challenges we see at the moment is, for example, how to bring in this picture devices that are not even able to run virtual machine or Docker containers and this type of services. So these MCUs where maybe they offer quite, let's say, even interesting computational capacity and processor that are dedicated to tasks like image recognition or artificial intelligence, but you cannot treat them as a, let's say, normal Linux because they are not that, as a virtual machine or so on. Do you have any idea of or plan for tackling that type of device as microcontrollers?
Yeah, in the past we use some edge device with Ubuntu or Linux operating system, and we connect with a remote shell in order to install or provisioning some application. But right now we're not making some progress with this, but maybe in the future we can use some IoT device with more capacity, like IP connectivity, web console or something like that.
Thank you very much, Antonio. I see there are no other questions, so I welcome on the stage Estela, that will present the work I2CAT is running for cross-domain network slicing and orchestration. Estela is a researcher in the software network department of I2CAT.
Hello, nice to meet you all. Could you confirm you can see my screen?
Yes, but you need to switch the view.
Exactly.
Yes.
So when you click on the configuration, the visualize, and click on it and take the other one.
There we go. Perfect.
Oh, okay, that's perfect. Thank you very much.
Okay, so yes, my name is Estela Carmona, and I am a research engineer in the software networks department at I2CAT Foundation. We are a research center, and we are specialized in digital technologies, 5G, Internet of Things, and artificial intelligence. Let's start with where I'm going to present our work on cross-domain network slicing as part of the Pleasure project, but let me first start with a basic introduction of the concept of network slicing. So just in case some of you are not quite familiar with it, why is it needed, and what are its advantages. So network slices are basically isolated partitions of network resources with certain performance and latency characteristics. And the main advantage of using network slicing is that we can deploy differentiated slice-based services on a per-use case basis. And that gives us isolation between services with different quality of service requirements, etc. Note that the definition of cross-domain network partition refers to radio access network, edge, transport, and core. And we also include compute resources at each tier. Also, by having a multi-layer architecture with open APIs, we can provide the necessary abstractions that we need at the intra-domain and cross-domain levels for communication between devices at different tiers. I'm going to talk about our approach to network slicing as part of the Pledger project. Our view is that it was important to develop a slice manager comprising the compute, the network, and the access network domains in order to allow operators to control and orchestrate services for different verticals in a seamless manner. And when I say operators, I'm also talking about infrastructure owners, for example. The main feature that we thought were interesting to have is, on one side, the dynamic provisioning of and instantiation of end-to-end network slices, including computing and networking resources. Of course, we need interaction with different virtual infrastructure management technologies for better support of multi-tenancy and multi-tier infrastructures. In our case, we tend to prefer OpenStack because it's quite a popular and powerful